Okay, so this is going to be a video on 14.1, the area between curves. So this is basically just the process of performing two integrals. One is going to be the integral of f, and then you'll be subtracting the integral of g. And so you'll take these bounds that were given here in this example of a to b, and you'll integrate over the difference of f of x minus g of x with respect to dx. And this gives you the area that you can see on this graph over here, represented as an integral. Now you can think of this as a slightly different sort of combination if you wanted. You could do AB of f of x dx, and then you could subtract your AB g of x dx if you wanted, sort of like I mentioned. And this allows for you to take the upper integral separately, integrate that, find the result, and then integrate g of x separately and subtract that from f of x to find what that difference is. So it'll give you different values, and you're just basically trying to find the magnitude of each of these integrals and then take the difference. That'll give you the result of this area between the curves. So do be careful about functions that dip below the x-axis, because this g of x here, since it is going below the x-axis, would get a negative value for the integral for that portion. If you wanted to make that portion positive, you'd have to put a negative sign in front of it to indicate that. You'd only do that if you were dealing with some sort of absolute value type of operation, one where the distance to the value, the x-axis, is the important aspect, not the direction with regards to which side of the x-axis it's on. That was important. And so in this case, if we're trying to find the area for A, the actual direction does matter. And so we're not messing around with absolute values. We're not putting any extra minus signs on there. We just have our regular f of x minus g of x for this form. Okay, so that's area between the curves. If you wanted to look at another thing that we can do with area between the curves, the Gini index is an actual application that gets put into economics, as well as into finance and such. It's basically a way of trying to estimate the equality for the income of a particular demographic, whether it be a population of a nation, a county, a state, or just some particular demographic of a population, not necessarily the population as a whole. And so this represents the income distribution, which has been normalized to a scale of 1 for probability's sake. And so you have from 0 to 1 the probability, or the income scale, and then that's the x-axis. And then 0 to 1 on the vertical axis is how much they make relative to the rest of the population. And so if you're at the one up here, up at the top, as a high earner, you have a very high income compared to the rest of the people that are in the population. And so the rest of the population, which are down here, would have less income, and it would eventually start to level out, and everyone would start to have more equal income later on down in the Gini curve, until we get down to 0, where people who aren't making income are making $0. So relative to some of the highest earners, they would have a ratio of 0. And so that's the Gini index. That's how income is sort of distributed, or how it's represented in terms for economics. If you wanted to calculate the Gini index, this is the integral that you can do it with. It's the integral from 0 to 1 of x minus f of x dx. And so this just represents the difference between that y equals x line, which is blue there, and the f of x line, which is a curve that's just below the y equals x line. And so that's the Gini index. It's multiplied by 2 in order to make it on a scale from 0 to 1, because if you had just the triangle down below, that would just give you an area of 1/2. So the 2 just normalizes it. All right. So that's everything for 14.1, and I'll see you for 14.2.